features and constraints, and we'll talk about some of these trade-offs. So there's not much deep math here as much as there is some real world decision making, the hacks, trade-offs, pipelines. So yeah, let's get into it. So two things: why all of this matters in practice, and then some of the uh, like optimizing models, like what it entails. So again, in theory, you might train a model and optimize it for accuracy. You may have uh, gotten resources, GPUs when you're training a model, but in practice, you ship it to a phone with 2 GB RAM. Maybe if you're using a newer phone, it's 4 GB RAM, but that's still like you cannot compare the two. So companies don't care just about performance, they care about cost, latency, and reliability. And in today's talk, we'll bridge that. So from a trained model to a deployed reliable system. I've seen models that work perfectly in Jupyter notebooks, but crash when deployed to real devices. So one time a model that predicted fleet route deviations needed to run on an edge box with one core and 512 MB RAM. We had to completely re-engineer it because this is the real world, right? So some context about fleet and edge device. So the company that I'm currently working in, Motive, so it's a US based MNC. What we do is we are a fleet management company and we also have hardware devices. So basically in the US, there are these trucking fleets. So let's say FedEx, they are a big fleet of trucks. So logistically, then we give them hardware devices like their dash cams and their ELD, which is a logger device for trucks. So these are the edge devices. And you may think of edge devices as also mobile phones, smartwatches. These are also industry edge devices. So what we mean by edge devices is something that's not running on our server, but on someone else's device. Before this, when I had worked in a research lab, that was also closely related to computer vision, but that was server side. So if we got some request, we were sending the response through API. So that's server side. On server side, we don't care much about resources because we have our own resources, our own compute, our own electricity. But let's say if you have a edge device in a car, in a dash cam, you won't be having much of these resources. So yeah, these are in the slide also, same things are there, real world constraints, shipping requirements, and so on. So this journey begins with making the model lighter. That's our goal. So let's start with model compression. Model compression techniques. Why is it necessary? Is there any industry example? Uh, when your model is too slow, too large, or too power hungry, you compress it. There's no one size fits all, but let me walk you through some of the most used methods in the industry. So these are pruning, quantization, and distillation. I'm sure you know theory of all of these, but we'll go over this and we'll focus more on the case studies. So we'll look at where they work, where they go wrong, and how we evaluate success. So academic models are usually trained on clusters with GPUs and evaluated on validation accuracy. But when you're shipping, accuracy doesn't matter that much if the user waits too long. So even when maybe you are using LLMs, you would rather go to GPT 4.0 or Claude 3.5 versus Claude 4 if Claude 4 is taking too much time. So as a user, you value your time as much as, or if not more, than the accuracy of response. So let's begin with pruning. Yeah, sorry, skipped a slide. What is pruning? So pruning is like removing dead branches from a tree. Many weights in a trained network are near zero. You can drop them. In research, people do unstructured pruning, but in production, we use structured pruning because it's hardware friendly. So let's see an industry insight here. Meta sparsity library even auto prunes while training. So you shouldn't expect miracles, of course. There is custom loss and prioritizing important filters is important. but it's a good library, that framework that you can use. It's not that difficult to use with your systems. Another way to shrink a model is not by removing weights, but by using fewer bits to represent them. Uh, that's where quantization comes in. So imagine replacing 32-bit float weights with 8-bit integers. You get faster inference and lower memory use. So quantization is always used in mobile edge models. So the trick is to calibrate it properly. You need some representative data, but you need to be careful because not all ops are quantizable. Hardware supports matters, and especially on edge devices. So let me give you an example. I once forgot to run calibration before quantization, and model passed offline tests but failed completely when exposed to real inputs. So the lesson there was always include calibration batches that reflect deployment data. Uh, I will share these slides. So even if I'm like skipping through some of these, like what's TensorFlow Lite or NVIDIA TensorRT, then you can uh, probably go over them later. All what is static versus dynamic quantization. I know all of you know. Uh, so let's also quickly go over knowledge distillation. So knowledge distillation, training smaller models using outputs from larger models for efficient deployment. I'm sure everyone has heard the student-teacher analogy. So in NLP, this is a favorite of everyone, and we have a case study for this in the next slide. So the trick is here again the student-teacher analogy. Use soft labels from the teacher to guide the student. It's especially useful when you need real-time inference, but you still want decent accuracy. So in for this, we had worked on our research lab, and one of our papers that was published in NLP. Actually, we used a lot of knowledge distillation in that. Uh, so yeah, let's go over this case study that we see here, Hugging Face Distill Bird, and we'll see how impressive knowledge distillation can be. And now this is the first slide where we see some of those trade-offs. So I'm sure most of you have used at least BERT, if not Distilbert, BERT, Robota. Like for NLP, like these are our favorite, right? If we have a Hindi transliterate database, we always go for Robota. So let's look at BERT and Distilbert and the comparison. Distilbert achieved nearly the same accuracy as BERT, but runs 60% faster and uses 40% less memory. This made it possible to deploy NLP models on phones, web apps, and your smartwatches. So on your smartwatches, BERT won't run, but DistilBERT would run. And the accuracy is 90% of BERT's accuracy. So like these are the trade-offs that you do. So maybe you won't use it for sophisticated DistilBERT for sophisticated use cases where accuracy matters a lot. But say QA chatbots, 100% use it. Like you have just 3 or 4 streams in QA chatbots. Okay, if the user asks this, go here. If the user asks this, go here. Like, it's a no-brainer that you go with Distilbert in those cases. And this is one of the big success stories of knowledge distillation. Um, let's look at some other trade-offs. Okay, these are some of the other trade-offs: weight sharing, low rank factorization, NAS, which a lot of things are happening in NAS. Uh, like if you just go to Google Scholar 2024, you'll find a bunch of NAS papers that are really intriguing. Compression trade-offs to Okay, so let's look at some of the compression trade-offs to consider. So weight sharing reduces parameter uniqueness. So more than one parameters are sharing weights. Low rank factorization splits large matrices. NAS finds efficient architectures by itself. But the important takeaway, every compression method trades accuracy for efficiency. So you need to choose based off of your constraints. What are your constraints? And is it memory? Is it speed? Or is it platform? So let's look at one of the real world examples. So Google's STPU uses NAS optimized models to find architectures that run efficiently on custom silicon. NAS isn't magic, it's expensive to compute, but given massive gains when deploying at scale, it's worth it. Uh, we have another Google Google real world example case study later for the next half of the presentation. We'll look at Google's Waymo there. Here we looked at Google's HTPU. So now we know how to make our models smaller. Now we know what to optimize for when we are in our R&D phase, where we are just optimizing for achieving the best benchmarks for our models. And then when we are shipping them, we know how to make them smaller. We know what to optimize for them. But this is still one step ahead of the curve. So we are talking about, okay, we'll train a model, we'll use this many resources, and so on, and how we'll deploy that model. But what do we train models on? We train models on data. And what if we're struggling with data set? So a good question, like, so I've worked very recently on something like this in a like intra-company hackathon that we had, and our team got the second prize in that. So like when we chose this, even I was thinking the same thing that you would be thinking, like, how can data be less, right? Uh, we have heard this quote, data is the new oil, and we are 7 billion people, like 4 billion people on the internet. How is this possible that we need to augment data? So I'll answer that question and what I learned in that project. But let's look at some of the data augmentation practices. So I'm sure all of you have tried this in code. Uh, okay, sorry, I clicked on it. Okay, so this basic techniques, I'm sure all of you have tried. So uh, maybe in MNIST data set or some other data set, cat, dog classifiers, flipping, rotating, cropping images. Like we used to do this. We did this in our third year in one of the labs where we used to flip, rotate images, then pass the images through classifier, and then check if the classifier is able to classify the image uh, as such. That was one of our assignments. So I'm sure all of you have tried this. There are some advanced approaches here as well, which I would recommend you to try because like these are, you don't need to reinvent the wheel, right? So you don't need to come up with your own algorithm where, okay, if it's a X by Y pixel image, we'll take this many pixels from this image and this many from this, and this will be the strategy of taking pixels and then see the classifier. We have those techniques, cut mix, mix up, and auto augment, Google's auto augment. These are like outstanding to try and like very easy to try as well. It's just plug and pull. So plug and play. So you can do this. Auto augment, by the way, has shown superior performance in ImageNet training. Going forward with that, there are more applications, and this is where, okay, let's talk about how can real world data be missing. And okay, we can see manufacturing applications and caution over augmentation that we would need to worry about. But so our use case was that we need to create a hazard detection clue. So based off of human heuristics before it actually happens. So what I'm talking about is we discussed that we ship uh, dashboards for trucking fleets, right? So we know that truckers often they do long distances, often they do it without sleep, and often they're driving at the wee hours of the day. Now, what we are trying to build, and almost all companies that ship these fleet databases, all of them are trying for this, is hazard prevention. Okay, so what are the human heuristics that you can see and detect that, oh, like a tragedy or an accident may be about to happen, right? So what do you, okay, like let's actually, like, let's try to brainstorm here. uh Let me see the chat. Okay. Yeah. Okay, I am not able to see the chat myself, but what I'll ask is if some of the admin can, if we get any response, then someone from the admin can uh, pass it on to me. So my question is that you, this is a, like, let's say, thought experiment. So let's say you are an engineer and you are designing one such feature in a car dash cam, right? And the statement is very simple. The problem statement is very simple. You need to design a hazard prevention model where you see heuristics from the driver, and then from those heuristics, you try to think that, okay, this is a good sign that an accident may be about to happen. So you are given the driver cam, you are given the road cam as well, and the rear cam as well. So you have these three views. You can see the driver, you can see the road ahead, and you can see the road before. So my question to you is, what do you think would be these clues or giveaways that you would focus on? That you look at any of these three views and you're like, okay, an accident may be about to happen. What do you think could be those heuristics? So you can type your answers in the chat, and then we can. Oh, my voice is not proper. How for how long has this been happening? Okay, okay. I'll repeat the question. So the question is, we'll talk about data augmentation and synthetic data later. So let's keep it out of it. My question to you is, you are an ML engineer for a company that builds car dash cams. Not just car dash cam and rear cam. So the view that is available to you as an ML engineer in your cloud, let's say, is you can see the driver cam, you can see the road in front of the car, and you can also see the road in the back of the car. Okay, these are the three video feeds available for you. So now you need to design an ML model which will take hints from either one of these three cams or views available to you, maybe something that the driver is doing, some clue that makes you classify this thing that is happening that is dangerous. Okay, if we don't do anything about it, an accident may happen within the next 5 minutes. Your model has to do that. So my question to you is, what will be these things that you want to label? Like, what are the things that you may think are clues? So I will give you one very easy example, like which everyone would have thought of, and then maybe we can discuss some other examples. One is if the driver is yawning too much. If the driver is yawning too much, you will know that, okay, this is one of the clues that we can optimize for. Like, this is one of the things that we can train our model based off of, right? Okay, what kind of yawning does a driver do, or how often does a driver yawn before such accidents happen? So what other clues can you get from these three views? I hope this time uh, I was audible. Good, good point. Traffic light. We can see if the driver has skipped a traffic light. That's a good, very good point. So if someone jumps the traffic light, you know they are not adhering to rules. Okay, very nice. What else? a car speedily coming from behind. Okay, true. But okay, I will reframe this in a way that we are looking to alert our driver or our fleet manager, someone who can call the driver. So yes, a car speeding is if a car is uh, coming really close to your vehicle, then it's a issue. But what I would say is tailgating or last moment lane changes by our driver. So what I mean is if our driver is tailgating, if our driver is going very close to the truck or the car in front of them, or if our driver is overtaking some other car, changing lanes by leaving very little distance between the two. So that then also you know that the driver is not being careful, right? Those are also things that you can get from one of these three views, which is similar to what Rinky suggested. Anything else? Anything on the driver? One is yawning. What else can a driver do which will be a giveaway? Yes, blinking eyes. Very nice. If a driver is blinking eyes constantly, or the blink itself takes a few seconds. So when you are sleepy, right, your blink takes more time than if you are not sleepy, right? So the blink of the eye can also tell if the driver is not attentive. One other thing I will share is if the driver is smoking, that is also so a lot of the drivers they like to smoke while while driving these fleets, which is definitely like it's against the law. But also this is also a major cause of accident. So yes, these are like all very good suggestions. Thank you so much. Um, okay, so now we know as a ML engineer, again in those shoes, now you know that okay, these are the parameters that I want to look for, and these are the things that I want to train my model for. So what will you do? You'll go to your cloud. You'll see, okay, in my cloud there is let's say 250 TB data of drivers who have given access or fleets who have given access to us. Now, what you need to do is you need to have an annotation team. Let's say you have 5 to 6 people in that annotation team, and their job is to annotate these videos with these labels. So, what will be our labels? Tailgating, smoking, blinking, yawning, lane changes. So, those people will look at these videos. Maybe they will, uh, maybe they will furthermore divide these videos into 5 second or 10 second videos out of that live stream. And then they will label these things. Okay, this driver was blinking at this rate. This driver was yawning. This driver has tailgated because at the end you want to train a video model. You want to train a model that sees a video and classifies it as whether dangerous driving or not dangerous driving. And I kid you not, we did the same thing. We looked at our annotators, what they had given in our database, and there is not enough data. So we work with FedEx, we are the second biggest fleet management company that provide dashboards, and there is not enough data for any of these things. Because as accidents, we would like them to be more rare, we would like them to not exist, but accidents in and itself is a very rare thing. So then you have two options as a company. One is you pay actors to do these things for you. Actors wearing different accessories. Someone is wearing uh, specs. Someone is wearing goggles. Someone is smoking. Someone is having pen in their hand because we want edge cases as well, where a pen maybe taken for a cigarette if we you don't train the model nicely, right? So either you go through all of that process or you create synthetic data. All of that process is time consuming. It requires a lot of capital, and you the overhead of work is too much. Or you create synthetic data that we did, that Google did, that a lot of these companies, Tesla did do. and which is what we'll be looking at in these slides. Um, yeah, so we are at the final, like I would say 2/3 of the presentation is done. We are at the final 1/3 where we talk about synthetic data. Okay. Yeah, but one thing that we must keep in mind is caution over augmentation. We do not want to augment the data so much that it leads to noise. So let's go over the next slide. Okay, so let's look at some of the traditional uh, data augmentation practice as well as enhancing text and tabular data because we just talked about video data. Just a point on the previous one. So in computer vision, we don't have enough varied data, so we augment it, rotate, flip, crop. But there are newer methods like cut, mix, and mix up, and auto augment, which is developed by Google as well, right? Uh, there is one research statement that my friend was working with, and the team he was working with tried aggressive rotation and flips in medical images. And turns out rotating X-rays by 180 degrees make no biological sense, right? So, and that broke the diagnostic model. So you have to augment data in ways that preserve semantic meaning. Uh, they were able to do much better with other techniques, but data augmentation did not work for them. That works well for images, but now let's see what works well for text and tabular data. Again, I will share these slides. So if you look at some term like let's say SMORT and you don't know what that is, then it's just minority oversampling. But if you like think these are jargons, like I'll share these slides so you can just Google these terms. All right. So for text, we use back translation, translate to another language and back to get natural variations. Okay, that's self-explanatory. In tabular data, we use SMORT. SMORT generates synthetic rows or rare class oversampling like fraud detection. LLMs can even generate full CSVs based on prompts now, but you need to be mindful of distribution drift. So you can't synthesize what isn't real, right? You can't synthesize uh, a driver taking a bath in the truck. Oh, okay. If a driver takes a bath in the truck, that's also definitely going to cause an accident, but that's not a real world scenario. Okay. We tried a GAN-based augmentation for fraud detection, uh, but some synthetic rows had impossible values, like it would have negative fuel, right? So you need some post-processing circuit breakers, rules to make sure that the generated data it's realistic. You can't uh, trust the synthetic data that much also. Uh, Prompt tuning you know about, so I'm going to skip over it. Uh, Okay, so we do have some deployment specific augmentation. So I've picked up these things from the internet. I don't have a personal experience in uh, either medical imaging or okay, I had some personal experience in edge models, but nothing in auto ML or medical imaging. But these are some of the well-known examples from the internet. So augmentation isn't just about boosting accuracy, it's about aligning with deployment. In healthcare, as we said, rotating an MRI isn't meaningful. In robotics, lighting and oculation matters more than pixel flips. So we also augment telematics data in ways that reflect driver behavior, not just noise. So we had one augmentation pipeline that worked great on benchmarks but introduced unrealistic noise in sensor data. It made the model miss sudden stops. So think like a domain expert when you augment. Like think of these thought experiments that we also did, right? Think of these thought experiments when you're augmenting data because they'll be useful. Like the R&D process begins with a lot of brainstorming first before doing anything. Okay, so let's dive into what we have been building up to so far, which is synthetic data. We've talked about most of this, but just a one-liner description would be real data is expensive, limited, hard to annotate. So we simulate it. By the way, if you're simulating something, you don't have to annotate it, right? So if I'm simulating driver smoking cigarette while driving, I won't annotate it. Right? My prompt was the annotation. Self-driving cars simulate millions of crash scenarios. Defense applications generate synthetic terrains. Uh, it's a game changer in privacy-sensitive fields like finance or healthcare, where you do not want to take data from your customers. So that in those fields, it's a game changer. Regulations also come to place here, and this is as industry as it gets. Okay, while you are doing research, you don't have to worry about this at all. But regulators keep a very close eye on how you're using your customer data. Even if you're doing building a feature which will benefit them, you can't make that excuse. So regulations like GDPR and HIPAA make synthetic data attractive because it can be realistic without being real. But you need to worry about the opposite regulators as well. So, like if you are using Instagram and you have opted out of using your data, like by default, it should be that you are opting out of using your data. Although the Senate hearings tell us that the story is completely different. But what I'm saying is, in industry, regulators are keeping a close eye on you. And if you do something, okay, Instagram may be using our data to improve our feeds, improve the recommendations that we are getting. But if we have not consented to that, that shouldn't happen. And these are the kind of challenges that you will face in the industry. Uh, okay, this is the this is the second case study that I wanted to talk about, which is Waymo. So Waymo is in news recently quite a lot because Tesla also started their robo taxi in Austin. So I'm sure so I picked this example because it's very relevant uh, today. And Waymo's use case is also similar use case as we discussed for our thought experiment, for our driver safety, but at a much larger scale. Because these cabs, they want to drive themselves, right? So it's not that someone is sitting inside and you can just alert them and save their lives. Don't get me wrong, that's like the most important thing that you can do as a software engineer, right? You can say, okay, I built a model that saves lives. But what Waymo does is that into to the power thousand. So in these cases, synthetic data is really helpful. So again, we can do this thought experiment. If my car is going too close to the pavement, what should I do? In real world, you won't find that many stock videos of these, so you need to generate these videos. It reduced their costs. Uh, it reduced their cost overhead tremendously, and they use simulation platforms like Carla and some internal simulators as well. You can read much more about them in Google's Waymo blog on synthetic data. I will uh, give a link to it in the references. Okay, how synthetic data created? One of my favorite topics to study in in my uh, in my time as a computer science student was GANs. Sorry, yeah, generative adversarial networks. Like it's so funny to me that one model is trying to trick the other model, and the other model, in the process of not getting tricked, is making the generator better. So one way to do this, have the synthetic data, is GANs, generate realistic faces or scenes. Another is simulation. So what we discussed in our case study, Carla and Unity simulate driving humans weather. Even prompt-tuned LLMs are now used to generate documents or conversations. I'm sure all of you have played around with that. Each of these has trade-offs. GANs need training, simulations are hard to scale, and LLMs hallucinate. We also experimented with Unity to simulate truck driver fatigue events. We then overlaid those on real camera footage to create a hybrid dataset. This reduced our need for costly hiring manual actors to do these things for us and manual labeling. This is also a very important slide. Now you have created, let's say you have created this synthetic data. How do you know it's any good? How do you evaluate that this data that you have gotten, it is at par with the real world scenarios? We often use statistical tests like the freshnet inception distance or evaluate end task performance. But there's no perfect score. Like you can't say, okay, if it reaches 85 out of 100, it's good. If it doesn't, there is a lot of context. It's very subjective. So sometimes synthetic data looks very real, but fails in production. So you need to validate it with real world generalization in mind, even if it means keeping some real data for testing. So what I would say is have a hybrid data set. That's the safest way to go. Uh, Again, like I've seen this in, I'm forgetting which, it was some Medium article of, I think it was OpenAI, but not sure. So where they built synthetic validation, which passed with flying colors. Synthetic data, which passed the validation test with flying colors, but it failed on the real data set. I think it was Sora, if I'm not wrong. So visual realism isn't enough. Field testing on real environment, that remains critical. Uh, I think like, so we are done with the theory, really. Uh, we are left with the final 2 or 3 slides. Uh, these are like some of the things, you can take this slide as references. So these are some of the things that we mentioned in the course of this presentation, right? So I have linked these things here. You can take a look at it. Some of the Google notebooks for these things are also readily available. So you really have to plug and play, and that'll be enough. So, like, writing code has gotten so easy that your job now is just to brainstorm. And if you have thought of something, you can implement it, rest assured. So, yeah, I mean, these will be some good things to dive into. Also, I had some uh you can say like assignments. Okay, you can look at this in your own time, yeah, right? Takeaways and practical advice. This is kind of the summary of the theme that we focused on, right? Uh, Q&A and resources. Yeah, these are the links. I have given my contact info in the first slide as well as in this slide. So we can really take a lot of these discussions offline. So if you're building something and you would like to like even discuss about that or something in the slide that you didn't understand, like um, I'll be more than happy to oblige there. I did have like a, I don't want to say assignment, but maybe some fun activity for you. So like please implement model compression techniques. Uh, it really helps if you have these things on your fingertips, right? Even in interviews. Adopt data augmentation strategies, and my favorite is utilize this synthetic data generation. Yeah, uh, that's all.